All right, well, let's go ahead and get started. Just so you know, we are recording today's session, so it'll be available to anyone later for you to revisit, to share with people that you know that, boy, you wish it had been on today to hear all this. Well, you can point them to it later. So we invite you to do that. So again, today we're kicking off a new webinar series in the spring that we're calling Data-Driven Agriculture. It's a weekly series on several different aspects of digital agriculture. And we hope that you really can join us each and every week, or at least catch the recordings later. You can go to the next slide. So of course, you can tell from the color scheme here that this is sponsored by Purdue, the Purdue College of Agriculture specifically. And so we've put two links there just for your reference, and we'll probably put those in chat for you later. But we have a Digital Ag Resources webpage that includes events like this, other things that are not always at Purdue, but they're just good events related to digital agriculture. We invite you to regularly check out that website for resources and pointers to our directory of people who are doing things in digital ag, as well as actual tools that you can access. There's a specific site related to unmanned aerial vehicles in our cooperative extension. And then also much of the work that we're going to have in this spring series is supported by the What which was a gift from the Lilly Endowment to the 10-county region here in West Central Indiana. Next slide. So these are the topics of the upcoming webinars, and I suspect that maybe because of the variety of topics we have, maybe not all of them may be of specific interest to you, but we hope that they are, so that you get some insight into the many realms in which data can improve the management decisions that we make, research questions that we answer, etc. So that's the series through March 25th. We've got one more slide that sort of picks up from there through the end of the semester. And so if you look at that variety of topics, we hope that several of these will be of interest to you. Most of the presenters will be Purdue faculty or staff. Occasionally, we're partnering with some industry folks who have like-minded interests, and we're in collaboration with them anyway. So I think you'll find some good connection to the real world through all of this. Next slide. So this is how it works. We'll have a presentation today. It's a live version. We'd encourage you, highly encourage you, to use chat. If you have questions or comments or resources that are related to today's topic, we highly encourage you to use chat to pose those questions. I'll serve as our moderator with Dr. Ackerson here at the end. And I guess as I do that, now I realize I failed to introduce myself. I'm Dennis Buckmaster, a professor of Ag and Biological Engineering at Purdue in the College of Agriculture. I also serve as a Dean's Fellow for Digital Agriculture, which gets me in some of these circles to facilitate some programming such as this. Next slide. Or I guess we're going to switch and now go to Dr. Ackerson's presentation. So let me introduce today's speaker. Jason Ackerson is a professor and assistant professor in agronomy here at Purdue. He came to us from Texas A&M. I think he arrived at Purdue in 2017. I won't give his whole biography, but I do want to just share a couple things. I and some colleagues have long dreamed, for those of you that love technical words, we have long dreamed for a three-dimensional, time-dependent, dynamic model of the world. And of all the people I know, Jason Ackerson is the one who can facilitate the making of that happen. He deals with spatial soil mapping and the related sensing that improves digital soil mapping. So he does three-dimensional X, Y, and Z coordinate, time-dependent understand. He is doing the work of time-dependent understanding of soil and its properties. So it informs our soil sampling strategies. He is a geospatial data guru. I've personally seen him do some instruction in one of our courses here at Purdue, AGR 333, which is data science and agriculture. He just is uniquely qualified with knowledge in both soils and data, three-dimensional data, geographic information style of data. So without further ado, we'll listen to Dr. Ackerson talking to us about the topic presented there. And then at the close of that, we'll do some nice Q&A and discussion with all of you in attendance today. Thank you so much for joining us.
Thanks, Dennis. I'm blushing after that introduction. I've never been fawned over so well. So thank you for that maybe undeserved introduction. So as Dennis mentioned, I'm a soil scientist, and my specific interest in soil science relates to understanding and better modeling and mapping the way soils vary in time and space. So today we're going to talk a little bit about precision soil maps and sort of the legacy of soil survey and how work that we're doing here at Purdue is helping move agronomic science past the reliance on traditional soil survey maps. Okay. So we're going to contrast what I'm going to talk about in terms of the research portion of this talk as digital soil mapping with maybe traditional soil mapping, which I've sort of tongue-in-cheek referred to as analog soil maps. So the effort of soil survey started really in earnest around the turn of the last century and really took off with the development of the Soil Conservation Service, now known as the National Resource Conservation Service. And they were tasked, as sort of the federal branch of the USDA that was tasked with mapping and quantifying the United States soil resources. And that task has really been a monumental work. And to this day, the United States has some of the best soil maps of anywhere on the planet. And just to give you an idea of how much information really is stored in these maps, the initial soil survey for Tippecanoe County was around 34 pages long. The next version, updated in 1959, was 124 pages. Then it was updated again in 1998, around 300 some pages, and now it's well over 500 pages of detailed property and spatial information related to soils. So if you've ever picked up an old, definitely now they're antiquated, but printout version of a soil survey, there's tons of work and tons of science that went into building those maps. Nowadays, we typically access those through Web Soil Survey. So if anyone's utilized the NRCS Web Soil Survey portal, the information stored there is being translated digitally, but it's really just a digitized version of those original, what we're going to call analog soil maps. And these were maps that were developed using a set of techniques I won't get into here, but it's sort of a conceptual way of thinking about the soils landscape and dividing the world into sort of discrete soil types or soil units, each of which has a unique set of soil properties or characteristics. And these maps have been used for quite a long time in terms of land use planning. They're used as inputs for hydrologic models. They're used for crop inventory, identifying prime farmland. They have a wealth of uses. But when we start thinking about 21st century agriculture and in the precision ag context, these maps kind of can fall short a little bit, both in their resolution, but also in the sort of static nature of some of the data that they contain. So as a sort of example, I'm going to look at some information from one of these USDA soil survey maps. And this is an 80-acre center pivot field. And what you're looking at is the average clay content of the soil units in the upper 50 centimeters of the soil profile. So this might be useful information for a irrigator who wants to schedule irrigation or do some precision irrigation, right? You want to put more or less water on different parts of the soil depending on the hydrology of those specific soil units. So if we go in and we drill a little bit deeper, one of the things you'll notice about this map is it really characterizes the clay content or the texture of this field into two main classes. There's the red classes that sort of are the high clay soils above 50%. So this is akin to feeling sort of like pottery clay. And then there's blue soils that are really sandy. Below 20% clay, it's going to feel almost like beach sand. So if you were to take this map at face value, you'd think that this field really has two strongly contrasting soil textures. But if we go and we do some observations from the field and we actually measure the clay content in these areas, we find that there's quite a bit of variability that's not represented in the USDA map. So the dots here represent places where we've actually gone out and measured the texture, measured the clay content, and it's on the same color scale as the background map. So you'll notice there's plenty of areas across the map where you have yellow and green soil textures, these sort of intermediate levels of clay content that are different than the underlying background USDA map. So this is sort of indicating that the information embedded in that soil survey map is not really complete or a real representation of what we see in the world. There's quite a bit more variability than we see often in these maps. So this sort of leads to the problem of, if we need to use precision soil maps for things like variable rate applications of fertilizers or lime, maybe soil-based management zones for precision agriculture, or adopting things that some of my colleagues are calling precision conservation, where you're tying conservation practices to the underlying soil variation. We need useful or soil data that is at the resolution or precision of those management strategies. And right now there's a mismatch between our traditional or analog soil maps and the scale at which we can actually manage these landscapes. So we need tools that can help develop sort of precision soil maps that give us the level of detail we really need for 21st century agriculture or digital agriculture. So one way we can get there, and this is a pretty common method, and anyone who's taken a basic GIS course or geospatial science courses has probably done something like this, which is just basic interpolation, right? We take a bunch of measurements from a field and we use some statistical interpolators, either inverse distance or Kriging or nearest neighbor, something in that neighborhood. And we can draw a sort of smooth map of what that soil variation might look like. And this is a really useful tool. It's used a lot in precision ag. People do this often with grid soil sampling for predicting or interpolating maps for liming rates or pH maps. But one of the challenges with interpolation is that it's really data hungry. You need a lot of points to make a useful interpolated map. And this is where we see the sort of need for other alternatives. So just to give a little bit background on interpolation for those of you who aren't familiar with it, I'm not entirely sure what everyone's background is here, but in interpolation, we can sort of simplify it. Instead of looking at a two-dimensional interpolant, we're just going to look at a sort of really basic 1D interpolation. So if we're looking at sort of interpolating the clay content along this line, what we might do is we might go out and say at 4 locations, collect a soil sample and measure the clay content at each one of those points. And then we can sort of think about an interpolant would be to guess what the clay content would be at an unknown 5th location. And if we sort of draw this out graphically, now we're sort of looking along that transect in the sort of x-axis here along distance, and we can graph the clay content sort of in a one-dimensional transect. And it might look something like this, where on the west end of the transect, we have high clay content, which sort of decreases towards the center of the transect and then ramps up and increases again at the eastern edge of the transect. And a sort of really easy way to think about this is an interpolant would just draw a smooth curve between each L3 of those points, and we can then predict the new location designated here by the dashed line and the question mark and estimate or infer the clay content at that location. And any interpolant you're doing, be it inverse distance weighting or Kriging, is all essentially doing something akin to this sort of estimation. Now, the limitation of interpolation really comes from its need for lots of data. So in this case, we're showing about 100 soil samples in this field, and they can make a pretty good interpolated map. But what if we only have a smaller number of samples? In this case, we're taking that same one-dimensional transect and actually simplifying it to just 2 points, right? So the obvious way to interpolate between those 2 points would be to just draw a straight line between them, right? We have no information between the points. Our best guess would be a straight line between each point. And in this case, we get a very different value of our estimated or interpolated clay content because we're now relying on that straight line rather than the curve we saw in the previous example. And this leads to some errors where we might over or under predict data in that interpolator, strictly based on the fact that they're not capturing all of the variability we would see. So although interpolation can be a really useful data format, it's often really data hungry. So it requires lots of observations, which can get really expensive and cost prohibitive for most users. So we need other tools that can be maybe a little bit more parsimonious with their data. And this is where we'll bring in the concept of digital soil mapping. So we can contrast the two. We can think about interpolation as using observations, and the distance between them is the main input data for our estimate. And you can sort of draw the analog to, it's sort of a statistical guessing where we're sort of saying, okay, here's where we think the most probable value for this new location is based off of previous observations. Digital soil mapping takes a similar approach, but instead of using just the correlation between observations in space, it's also going to bring in additional environmental data. And we're going to use that correlation between measured soil observations in the environment to do what's something that's more akin to a statistical prediction or an empirical model of the spatial soil distribution or the spatial patterns we see in soils. So a sort of breakdown of the digital soil mapping paradigm would be to think about sort of two sets of data that we're going to sort of mix together in some modeling framework. So on the left-hand side, we see sort of a cartoon of what might be a stack of raster data representing the various environments in the field or the watershed that we're thinking about mapping. And at specific points in that area, we might make a soil sample or take a soil sample, make a soil observation, and then we can correlate that environmental data with the soil sample through some sort of empirical model. This could be really simple regression framework all the way to more complicated sort of machine learning approaches. And that gives us a sort of digital soil map or prediction of the probability or the most likely distribution of soil properties in space. So to break that down into maybe another way of thinking about it, we could first start any digital soil mapping process by identifying our data need. What sort of information do our end users need? And then we collect sort of that's two pieces of data again, some soil observations. These are usually point data, measurements of soils, and then some environmental data that defines or characterizes the environment we're interested in. And then using some sort of empirical model, we can get to a property map. Now, the sort of key aspect to this process working is we need both two really useful pieces of input data. First, we need good soil samples. So these would be sort of traditional laboratory characterized soil data. And then we also need good, what we would call environmental covariates, or data that describe the pedologic or edaphic environment that those soils are formed in. And sort of another way of thinking about this is we're thinking about soil as a function of some sort of environmental and management input. And the trick to digital soil mapping is estimating what that function is. So in a really easy example, I think it's tangible for a lot of people in agriculture, is to think about soil organic carbon or organic matter. In Indiana, we see that there's a really strong link between organic matter and soil drainage. Poorer drained soils tend to contain more organic matter. The decomposition is inhibited, and over sort of soil formation timescales, that leads to an accumulation of organic matter or organic carbon in the soil. So we can think about soil organic carbon as a function of soil drainage or the soil topographic relationship. And the way we might categorize that or quantify that in a really simplistic digital soil map or digital soil model would be to model soil organic carbon as a simple linear function of something like topographic wetness index. And that's a derivative of sort of a digital terrain model that we know is associated with water holding or water storing parts of the landscape. So we can model that as a really simple linear model between a observed environmental parameter, topographic wetness index, and a measured or observed soil outcome. So the trick in any digital soil mapping program is to really take those two pieces of data and find the best model that describes the relationship between the measured or observed soil property and some measurable component of the soil landscape. So the types of environmental data we use are really varied, but the key piece to any covariate is that it needs to be easy to measure. My favorite types of covariates are free or publicly available data. They often cover large areas, and they're typically in some sort of raster format. We don't want point data. We want data that's measured everywhere across the landscape we're trying to predict. And last, but certainly not least, we want to have some sort of idea that those environmental data are correlated to the soils we're interested in measuring, or the soil property of interest. There's plenty of raster data out there, but it's not all correlated to soil properties. So we want to make sure we're starting from that point. So types of data we often use in this structure, Landsat or satellite imagery is a really common starting point for us. There's tons and tons of freely available satellite imagery of both bare earth and canopy filled in sort of crop filled landscapes. And those are really good predictors of soil patterns. And in this sort of frame, we're showing Landsat and Google Earth images from that center pivot irrigation field we looked at earlier. And we see a very strong correlation here between the reflectance measured either from the Landsat or Google Earth imagery and the accompanying soil variation. Other things that are common and really being addressed here at Purdue are UAVs or drone imagery. This can be really useful in predicting variation in soil properties. And actually, both of these images are taken from folks who are involved in Purdue's extension efforts in UAVs. Yield monitoring data is another really common data source for us. Often we're thinking about mapping agricultural fields. And I've spent my professional work trying to develop better soil sensors from a scientific perspective, but often we find that the best soil sensors are the crops we're growing in the field. And if we can measure the variation in crop yield or crop response across the field, it often is really tightly coupled to the soils and gives us really good input data for soil maps. And last, but certainly not least, would be LIDAR or digital elevation models from either LIDAR or SRTM data. And these describe the surface elevation of the landscape in relationship to the surrounding environment, right? So these are, you can think about these as a digital topographic map. And in Indiana, we're blessed to have really high resolution LIDAR products from across essentially the entire state covered with really high resolution LIDAR. And I love this picture because it shows our Agronomy Center for Research and Education here in West Lafayette. And if you've ever had a chance to come out to Acre, you'll notice distinctly the sort of rows or grass pathways between different plots and fields are really highlighted in this LIDAR data for Acre. And what's interesting about that is if you go out and walk across the field, you might not notice that those roads are significantly higher than the landscape, but the vertical resolution on these LIDAR products is so high that we can actually find really small details. And all of that correlates nicely to various soil properties. So now that I've given a little bit of a background for the context and the why and how of digital soil mapping, we're going to go through sort of two case studies showing various levels of complexity of digital soil mapping projects. So in this first one, it's going to be a really simple example of a very basic empirical model to predict a useful soil property. So in this case, we're going to be using an environmental covariate derived from electrical conductivity, which is just a measure of how easily soils can transmit electrical current. And that's correlated to the soil's water content, salinity. If there's extra salts in the soil, it's easier for it to conduct current, and the clay content. So the higher clay content, the more charges are able to translate along the soil's surface, increasing its electrical conductivity. So we can map this in various ways. Commercially, this is often done with an instrument called a Varus, which uses a set of coulters that actually drive a current through the soil. But in this case, we're mapping electrical conductivity with a electromagnetic induction sensor, which essentially is a non-contact way of measuring conductivity, similar to the way a metal detector works. So you can think about this as a fancy soil science metal detector. And in practice, we just drag this instrument across the field, it measures the conductivity and the geolocation of the sensor, and then we can go in and interpolate an electrical conductivity map, and then use that map for our digital soil mapping exercises. So again, we're going to show this example from that same center pivot field we've seen earlier. And if we look at the conductivity profile of this field, we see that it roughly matches the background soil color. So you can see that there's darker soils on both the west and the east end of the field, with the sort of lighter colored soils in the center of the field. And if we overlay that interpolated electrical conductivity map, we see again high electrical conductivity on the darker colored soils on the east and west edges of the field, and lower conductivity soils on the center section of the field. So in practice, we would go out and we'd collect a bunch of soil samples from this field, each represented by one of the black dots here, and we would extract the electrical conductivity data from that raster and associate it with the measured property at each one of those locations. In this case, we can look at the clay content of that field and correlate it with the electrical conductivity measured at each of these points. And this gives us a nice tight linear relationship between electrical conductivity and clay content. So here we're mapping clay content as a simple linear function of electrical conductivity. So now we have a way of converting that electrical conductivity map from conductivity space to clay content space. And it becomes a pretty straightforward mapping exercise. We're essentially just going to change the label on our color axis from electrical conductivity to clay content, right? So now we see that the blue areas are associated with low textured sandy soils, and the red areas associated with high textured clay soils. And it generally maps or follows the same patterns we saw in our traditional USDA soils map. So one of the challenges, or one of the benefits, excuse me, of digital soil mapping is we can often get by with a lot fewer samples. So instead of going out and collecting 100 observations in the field, we can do a sort of thought exercise of what if we only collect maybe 5 or 6 samples from a field. So in this case, we're just going to take our sample size and shrink it from 100 to 5 and see what that does to the resulting map. And in fact, we get a very similar linear relationship between those 5 subsetted points and electrical conductivity. Resulting maps are almost identical between a smaller sample size and a larger sample size. And this is one of the key benefits to digital soil mapping over an interpolate. With 100 samples, we could draw a pretty accurate interpolated map of the soil properties, but we could not do the same thing with 5 samples. So as long as we collect our samples in a sort of stratified approach, we end up with reasonable predictions of those soil properties. And again, we can compare a larger sample, 62 samples in the original exercise with a subsample of 5 samples. And those lines are statistically identical. The slopes and intercepts are not statistically significantly different from each other. So regardless of the sample size, as long as we have a tight relationship between our environmental data and our soil property of interest, we can draw really good correlations between them in really accurate maps. And this is, again, the benefit of digital soil mapping over interpolation, is we can reduce our reliance on large sample sizes and get by with fewer samples, provided we have a good relationship between the covariate of interest and the property of interest. So that was a really basic scenario for digital soil mapping, a really easy project of empirical modeling with really, really simple maps. And if you're a data person, you'll realize that all of those graphs were actually Excel graphs, right? You don't need any sophisticated data science techniques to draw out or make those relationships. They can all be essentially done in Excel. But now we're going to move to sort of the more cutting edge digital soil mapping. And this is what I'm going to call the sort of PhD level digital soil mapping, where we're pulling in more complicated models and more complicated data streams. So one of the challenges to digital soil mapping is that oftentimes we're limited in the amount of soils data we can collect. Soil sampling is time consuming, it's often very expensive, and depending on the property you're measuring, those laboratory assays can be very expensive or really costly. The bulk of any digital soil mapping program, aside from labor, the expense for us is collecting the soils data. So what we're going to talk about in this next section is ways we can actually supplement or augment that soils data with cheaper to access sensors information. So in this example, we're going to look at using an alternative data stream known as visible near-infrared spectroscopy. And what we do is we can go out into the field and we can collect a series of soil cores. Those are denoted on the left panel here, and it's about a 2 1/4 inch plastic sleeve that we extract a core from. When we cut those cores sort of down their vertical axis, sort of exposing the soil profile. And then we can go along that soil profile and collect spectral information using a handheld VIS&IR probe. And that gives us sort of a reflectance fingerprint for each location in that soil profile. And that's denoted by the spectrogram on the right side of the screen. And each of those spectral reflectance profiles is unique to that particular soil in terms of its chemical and physical composition. And because of that unique nature, we can actually correlate the spectral properties to observed soil parameters. So in practice, what this allows us to do is instead of collecting laboratory data on our property of interest, we can actually infer that property from a spectral prediction. So in this case, we're showing on the right-hand side one soil profile where each white dot represents a place where we've collected a spectral observation using our VIS&IR probe. And then using that unique spectral data, then predicted the soil's organic carbon content. And that's mapped on the x-axis of that left-hand figure. And we can do that really cheaply for every location within a soil profile. So we can measure, maybe 40 or 50 observations within a single soil profile at a fraction of the cost of actually doing the actual laboratory data. And because of that, we can get high resolution profiles of the depth variability of various soil properties in space. This is a really cheap, really effective way of collecting lots of high resolution soils data without lots of costly laboratory assays. But one of the interesting things that we can now do with this data is because we're not only representing the soil variability as a single value at a point, but rather a depth changing value, we can actually start doing some really interesting three-dimensional mapping. So in this example, we're going to show you some maps developed using a full 3D mapping program. So on the panel on the left-hand side of the screen is sort of a elevation model for the field we are working in. It's essentially an 80-acre set of fields. And each of those arrows denotes a place where we collected a soil core, brought it back to the laboratory, and did our spectroscopy analysis on that. So each of those points has one of these organic carbon profiles with depth. So it's not just a single soil observation, but you can think about it as a smooth soil variation with depth. And we can mix that in with our environmental covariates. In this case, we used elevation data and some terrain derivatives, aerial imagery, and electrical conductivity data. And we mix those in a general additive mixed modeling framework, which develops a sort of three-dimensional splined interpolant of the soil property we're interested in this case, organic carbon. So we can take those depth profiles, combining them with environmental data, and we can generate a three-dimensional map or model of the organic carbon concentration in that soil. So in this case, instead of making a map of just one layer of the soil, we're mapping the whole soil entity in that field in 3 dimensions, sort of in a single step. So you can sort of take a look at this map. I don't have anything animated here, but we can make little animations and cut slices through this 3-dimensional body in the soil profile, looking at the various carbon concentrations. And that gives us an idea of where carbon's being stored in the soil profile, at what depths, and how it varies in space. And we can sort of cut different slices through that and look at maybe more traditional maps so that you can think about these as sort of top-down views of that same 80-acre field, looking at the median predictions for 0 and 30 centimeters depth. So darker areas are places with higher carbon concentrations. So we see that most of the carbon like we expect in a lot of areas, is concentrated in the surface. And then we can also, because of the framework we're using, we can actually look at the confidence interval around those predictions, and we can find where or not the model is more or less accurate in terms of its prediction of organic carbon. So we're moving closer to sort of Dennis's dream of a three-dimensional view of the soil landscape. So just to recap, if we couple that proximally sensed data, the visible near-infrared spectroscopy, and digital soil mapping, we can start moving towards high-resolution, temporally valid, high-resolution 3D models. Do we have some questions in the chat? I might take a quick second and take a look at those.
No, we're good to go.
Okay, cool. I was just getting notifications on my window here. So we've sort of shown you kind of the context of digital soil mapping, and then walked you through sort of two easy case studies for doing some digital soil mapping kind of in a research setting. But one of the things my lab also focuses on, and through my extension programming, is sort of improving the adoption of these techniques or these data for land managers. So thinking about challenges for digital soil mapping in the future soil survey, I think about those in sort of two main areas, and we'll show you ways we're kind of addressing those challenges briefly. The first is what I'll call the intellectual paywall. So the techniques we've shown you today, some of them can be pretty data and skill intensive, right? If you're going to go and do a sort of three-dimensional soil map, you really need to understand GIS, spatial statistics. You need to have some skills in computer programming. You need to have some good soil science skills to actually go out and collect the data. And that's pretty daunting if you're a CCA or a farmer who just wants to make a better pH map to do some precision liming applications. So there's a sort of barrier to entry to being able to do some of these DSM techniques sort of in practice. The other sort of area we focus on is that existing soil data products often don't provide information that is really useful directly to consumers. So they might have questions related to a land management strategy or soil property of interest that's not readily available in the existing soils data. So can we augment existing soil surveys using some ideas around digital soil mapping to provide better data products that are more useful to end users? So I'm going to show you sort of two quick projects relating to each of these challenges. So the first one is removing barriers to digital soil map adoption. And our approach to this is to develop easy to use tools for DSM. And this is actually a WIN-funded project that one of my graduate students is working on right now. And essentially what we're doing is building a open source digital soil mapping toolbox for the software QGIS. So anyone who has sort of rudimentary skills in GIS can load their data, process it through this toolbox, and generate statistically valid and usable digital soil maps. So we're sort of in the alpha stages of testing the software. We're hoping to have this done maybe in the next couple months. So if you're interested in being a beta tester, shoot me an email. I'll be happy to share the package with you. But in practice, if anyone's familiar with QGIS, it works very similar to ArcMap if you're an Arc user, but it's free and publicly available. So you would load your data in, which is a common sort of way people would manipulate data for precision ag. And then simply download and load up this toolbox, and it sort of walks you through the steps needed to process your data, do some terrain analysis and manipulation of the data so that it's in a format that we can start using digital soil mapping tools with. And then it sort of walks you through the steps to prepare a statistically rigorous digital soil map, and then outputs a raster that you can then use for whatever process you see fit. So very excited to see that project moving along, and we're hoping to have useful versions distributed over the next couple months. So the other area we're working on is sort of to improve the utility of existing USDA data. And like I mentioned at the top of the talk, existing soil maps have tons of really valuable information in them, but it's if any of you are familiar with Web Soil Survey, sometimes it's really hard to extract that data out of those maps. And often it's not in frameworks that are useful. So one example that comes up a lot in the sort of extension programming I do related to soil health is looking at soil organic matter content. And a common question that people would have if you're interested in improving the soil health of your farm is how much organic matter is needed or should I expect for these particular soils? And in fact, Surgo has a data field for organic matter in it. So you can go to Web Soil Survey, draw out your field boundary, and it will give you a map of the soil organic carbon contents of your soils and give you sort of an idea for what those levels should be. So if we look down here in the rating tab, this looks at the percent soil organic matter, for the soils depicted in this map. The limitation for that is that it doesn't give you really a range of values. It gives you a single number, which doesn't give you much guidance on are my soils above or below this mark that I should be at? Where do they fall within a range of usable organic matter contents? So one of the things my lab has been working on is a soil organic matter viewer tool, which takes that same USDA data, kind of redigests it and populates it with useful ranges of organic matter. So you could go to any place in Indiana and query the soil type you have. And instead of providing you with a single organic matter value, it provides you with a sort of range of values, potential values ranging from good, medium to very good, right? So you can start bounding those soil organic matter values and give you some idea and some context to whether or not the data you're measuring from your farm or your field is higher or lower than you'd expect for similar soils across the state. So just to sort of do a quick recap before we have a Q&A session here, digital soil mapping is a sort of useful set or catch-all term for a set of geostatistical tools we can use to provide high resolution, up-to-date soils information. And that data is really useful for things like precision agriculture, conservation management and planning, and other digital agriculture applications. These digital soil mapping methods can vary in scale and complexity. I've shown you work, particularly here, working at the precision ag scale, the field scale, but a lot of the same ideas and concepts are being applied at regional, watershed, or continental scales even. There are groups around the globe working on continental scale or global soil maps, which are really interesting data projects and problems. And then our ongoing efforts here at Purdue and in my lab and in a couple other groups in the agronomy department are increasing the adoption of DSM practices and providing better sort of what I'm calling next generation soil survey products that really provide stakeholders with the tools and the data they need to make accurate and informed soil management decisions. So I think that's about it for my talk here. Hopefully we'll have some time for some discussion and commentary.
This is great. Jason, I wish I could just cancel the rest of my day and just have conversation with you about the things that you just presented, because you used a lot of my favorite words, things, simple equations, the ones that I can understand. And also the word free showed up a couple times, but mainly this ability to take some data and make sense of it, you know, to not necessarily always need big data, but sometimes small data used in the right way. I hope the rest of the audience is getting excited about the possibilities here. So if anyone has a question, feel free to put it in chat, or I can't really tell if you raise your hand very well. So maybe just say, I have a question in chat, and then we'll just invite you to unmute. But someone sent one just to me and maybe, just privately, so I'll ask you. Is the USDA mapping tool available publicly?
So right now, there's maybe some clarification from the question asker would be helpful, but USDA's soil survey data is all publicly available. But the tool we showed at the end of the presentation, we're sort of still working out some of the kinks, but that should be live on Purdue servers sometime within the next couple months. So be on the lookout for that. It should be out there soonish.
Sounds great. Great. That's I think that was spot on to the question. So I'm going to watch chat and see if another good one shows up here. But maybe to those farmers and advisors that might be on the line or watching this later recorded, even though a couple of these tools aren't really ready for prime time yet, or maybe I'm not, even though they would be, I'm not ready to use it yet. Like I need to go farther up the ramp of education. Are there things that farmers or their advisors could or should do better with regard to the data layers that they have, or their file structure of storing stuff? Like, how do they get ready for the next tool?
Yeah, that's a really good question, Dennis. And yeah, I think that's one of the things that's interesting in this space right now in digital agriculture. Really is, farmers for the last 2 decades in some cases have been curating really amazing data sets that have a wealth of information in them. And that's just right for the right CCA to come in and start doing some really neat analysis with them. So if I was going to give, sort of one piece of advice, it would be to really keep a good track of those data as they're coming in. So, it's hard when people are in the middle of harvest to think about data curation on your yield files when you've got 1,000 other things on your mind. But spending some time to make sure that data is well curated, labeled, and stored properly where you can have access to it is really useful. One thing we see a lot of times with these data coming through is that often they're stored without reference to their geospatial coordinate systems. So sometimes I'll receive data from farmers that are just a latitude and a longitude, but without the projection information in there. And that might seem like a trivial piece of data, but we have to actually make these data line up. So keeping track of your data in a format that contains the appropriate references and spatial references is really, really useful. And if you don't know what your systems are being stored in, spend a little bit of time trying to make sure that everything is being stored in the same format, because we can think about it analogous to different languages. And if we're trying to convert something from English to German, we can do that, but we have to know that it starts in English. And often in geospatial reference data, that's not as straightforward as just reading something and saying that it's German or English.
Good. So someone had sent me this question about, do you feel the spatial data models are comparable with Veris data? Are they better or worse? And how do we use them to make better new soil zone maps?
Yeah, so I think,
and Matt, feel free to clarify your question if you'd like.
Okay, well, so Matt, correct me if I'm wrong, but you're sort of asking the question of, how do these soil maps compare to data coming off of something like a Veris? It really depends on the relationship between the underlying soil property and the Veris data we're looking at. So, oftentimes if you're trying to use Veris data, really commonly used in industry to identify or delineate management zones. If those management zones are really related to soil properties, that can often be a shortcut to going through and managing it and doing a digital soil mapping exercise, right? You could estimate a management zone strictly based off of that Veris data. And that's a perfectly valid approach. Where it would get more tricky is if you're trying to then use some other data to estimate or utilize the soils data directly. So I have colleagues who do crop modeling or agronomic systems models, where they need to know how the soil properties themselves change in space. And that's really where we need something like digital soil mapping to get to that point. The other use case where Veris data might not be the best direct input for delineating yield zones is if the soil properties that we're really interested in managing with those yield zones are not really linear with relationship to that Veris data. So I showed you a case that I picked specifically because the relationship between clay content and electrical conductivity in that field was very nice and linear. But in some fields, it's not that way. Sometimes you have a sort of exponential or power function where a 1 unit increase in electrical conductivity might not always yield a proportional increase in that soil property, right? So if you change the conductivity by 1 unit, it might double the soil property of interest in one location or have it in another. So if those relationships aren't linear, the Veris data can be a little bit misleading unless you do some processing to that originally. I hope that answers the question. So sometimes you can get away without the DSM process, but other times it's better to understand that data. It all comes down to understanding the question and then the relationship between the Veris data and the soils data you're working with.
Yeah. So Rachel is asking about your recommendations, Dr. Ackerson, on online resources to learn about spatial statistics and analyzing rasters data. Maybe your top 1 or 2 suggestions of where to go.
Yeah, so there's a wealth of information online about soils data or analyzing rasters data in this format. There's a really good book published by a group out of University of Sydney on digital soil mapping. And that, if you have a university license, that's freely available. But there's some of the critical chapters are out there for free. So you could look, I think it's a Elsevier book, Digital Soil Mapping with R. That's a really useful topic. In the sort of paywall space, Purdue is actually working on a graduate certificate in spatial data science. Dennis could probably speak more to that, but that would be a really good resource for maybe more professional training. But other than that, looking into the sort of open source R and QGIS community, there's lots of really useful people out there. I mean, oftentimes I send my students links to YouTube videos when they have questions because there's so much good information already out there in this space. But if you have questions, feel free to shoot me an email and I can direct you to the right resources or give you some resources from my lab. If you're looking for specific things, be happy to help out that way.
Great. So I'm watching for other questions. While we're waiting, I'll just pose one more, and we're getting close to time, so I don't want to drag this out any longer than we should. But I'm sort of intrigued because of your deep knowledge, pardon the pun there, about soil. If you could only choose one, like you only get one more layer of data, would you choose soil survey, LiDAR topography, Google imagery, or 3 years of yield? Which would you rather have? Reminds me of a country song, actually.
So I'm going to do the very academic thing of answering your question with a question, which would be to think about, what actually problem we're trying to solve here. In some cases, soil survey data might be the best source of information. And as a soil scientist, I'm certainly biased to when I work in a new farm or a new field. That's the very first place I look, because I can sort of, knowing the soil types and the soil characteristics, I can sort of get a feel for the landscape pretty well. But that's my personal recommendation. If I were a CCA and I'm thinking about, making some management recommendations for a farmer, I might have a different approach to that. And I think, but probably the first thing I would look at from a CCA perspective is quality yield data is really probably one of the best sources of spatials information. But that's with the caveat that it has to be quality yield data. If anyone's worked with yield data in the field, they know that not all data is of the same quality. And sometimes bad yield data is maybe worse than anything else. So if you're going to get good data and you're working with a farmer that's having good data curation and calibrating their combine and making sure everything's up to snuff, I would take that 3 years of yield data. Without that, I would look to publicly available LiDAR data as maybe the next most useful piece of information.
Okay, thanks for that very good answer. And you, by identifying that there is the possibility of bad data, bad yield data that hasn't, that wasn't calibrated or corrected, or flow shift corrected.
Mm-hmm.
We do need to know, when do we have good data and when we don't have good data? That's the square one. And so you have convinced me that your feet are on the ground and you're doing a good job of helping us translate to reality here. So I personally want to thank you, Jason, and I know everybody that got to listen today appreciated the insights and the knowledge that you've extended. I just want to also invite everyone to join us at the future webinars. You saw sort of the schedule show up there on the screen. Same channel, same time, Thursdays, 12:30. We welcome you all back. Do we have one more closing slide there, Andy? And I also want to thank, in the background, you didn't get to see them, but Randy Trida and Megan Kuhn do an amazing amount of work to help these webinars flow smoothly. And so publicly want to acknowledge their effort in this too. So make a note of that particular link there. Of course, you may have been there already, and that's how you found this in the first place. But do watch for the future webinars, the recordings of previous ones. And we wish you all a very wonderful Friday. Do bundle up if you're in West or Central Indiana. It's going to be cold for the next week and a half. So bundle up, stay safe. We hope to see you back next week. Thanks again, Jason. Thanks, everyone.